Yes, yes, this is not nice now. I agree. Okay. Okay, thank you. Good morning. I work in the OGLE team, and OGLE is based at Warsaw University Observatory. And the Warsaw Telescope is located in Las Campanas Observatory in Chile, and the southern edge of the Atacama Desert. And this is the telescope and the operating room, 20 meters next to the telescope. And there you can see the beautiful stripe of the Milky Way, and the sky above Las Campanas is really impressive.
Outer space. Could you kindly remind what is the abbreviation of OGLE? There is an acronym of what?
Yes. Okay. Optical Gravitational Lensing Experiment. But right now we are rather a wide field survey. We do not concentrate not only on microlensing events, but on variability. Yeah, optical gravitational lensing experiment. So.
Nobody remembers what was under the name of BMW.
Okay. And this is an artist impression. This is of course not an image, and we will not take such image within few or more years or 100 centuries, because we live in the galactic disk, and as you can see, our galaxy is a spiral disky galaxy, so it's a complex, really complex structure, and we have galactic bulge in the center. We have the disk, so this is seen face on here, and with the arms, and then we have galactic halo. And galactic halo is relatively light. It has about 1% of the total mass, and galactic bulge is about 25% of the mass.
Accept the code of using colors.
Yes.
On those paintings.
Yes.
Or I mean, you don't see these colors. These are
yes,
these are computer graphics.
But it's usually blue indeed.
Okay, so
well,
in the center.
If this is a computer graphics.
Yeah, so
the only question is, I don't question that it's blue or red or green or whatever. The question is there a generally accepted code? Why on this picture something is painted blue or something is painted green or whatever?
Okay, so okay, so cool old stars. Red giants are in the center, and in the disk we have young stars, massive stars, bright stars, and usually hot stars. So that's why the disk is presented in blue, because in the light the bright stars dominate, and the bright stars are particularly along the spiral arms. And another thing is our sun here. So we are about 8.5, 8.3 kiloparsecs away from the center. So this is about 27,000 light years. And the problem for us is our location. So we are very close to the galactic plane, where we have, particularly in the galactic disk, a lot of dust, and that's why we don't see much. So we don't see much very close to the galactic plane, in the optical particularly, and that's why we know what's going on here in this area. We know something about the galactic bulge, but we truly don't know what's on the other side. So as you can see, this is actually mirrored in this image, the other side. Behind the galactic bulge, and this is based on near-infrared observations from Spitzer satellite, Spitzer mission and experiment instrument glimpse.
The scale of the picture, Spitzer satellite is sitting on the Earth.
No, well, yes, but
on the scale of that picture, it's equally well to say that it sits inside of the Earth. I mean, that's irrelevant. I mean,
Yeah.
if we don't see anything out of the galactical planes, this pizza radius orbit, it doesn't happen. So.
Okay, and now a short history of solving the puzzles in the last about 50 years. So in the 50s, after radio observation at 20 of hydrogen, neutral hydrogen at 21 centimeters, we were sure that there are spirals, that the disk of the galaxy is spiral. Then in the 1962 was this idea of the formation of the Milky Way, canonical model that from one cloud, the one cloud collapsed and relatively quickly formed, the gas formed the disk, and then stars appeared, and they are as we can see them right now. Then 1963 the first quasar was discovered, 1963. And it was quickly realized that it is located very, very far away at quasars are located far away at cosmological distances, and they are very, very luminous. So there was this idea that they are powered by black holes, active, very active black holes. And then in 1971, the idea that maybe, or very likely, such a massive black hole is located at the center of our galaxy, and it was identified with the radio source Sagittarius A star in the 70s, late 70s. And later, with different surveys, it was found that we can divide the stars in our vicinity into stars forming galactic halo. Of course, galactic bulge is further there, but we have halo stars in the neighborhood, and we have disk stars, thick disk stars and thin disk stars closer to the galactic plane, or on more circular orbits, younger stars. And then in the 1990s was this unusual discovery of the Sagittarius dwarf spheroidal galaxy. Something unexpected, a substructure in the galactic halo, and later another discoveries. And then people realized that this model is not true, and a better model, hierarchical model of formation, that the formation is continuous, that we have many dwarf galaxies falling onto the Milky Way, better explains what we see. Okay, so the view again. I will start from the center, and then I will describe the other components of the Milky Way. So the very, very center is very complex. This is combination of observations in X-rays, in radio wavelengths, and also near infrared. So you can see. So this is 3 parsecs that you have scale here, and you have different things here, like some kind of spirals. The gas forms and the dust forms spirals. Then you can see something like a nuclear disk, and then you have also stars at the center. So it looks very interesting, and in the 1990s people started to observe it with better techniques from the ground. And observing the galactic center is not easy because of the dust in the galactic disk, so closer to us. And with near-infrared observations and current telescopes of 8 to 10 meters in diameter, we can observe only the brightest stars. So right now we do not see stars as massive as our sun. And with spectroscopy, we even can see less. And this special technique used to observe the galactic center is the adaptive optics. And in future, we hope to see with the giant telescopes, or like the European extremely large telescope of 30-40 meters antennas or dish mirrors, stars fainter, and to see their distribution. But right now, what you know about the galactic center is that generally the area is old, so the stars are of few giga years, and they are usually red giants, so they are cool stars like AGB stars or red supergiants. But closer to the galactic center, there is more and more blue young stars, and you can also see it here that closer to the galactic plane you have a cluster of young stars, and this cluster is called the nuclear cluster. And what's strange with this cluster is that it's very young in the old galactic bulge. So you have really young and massive stars there, and it's hard to explain the presence of such cluster at the very center of our galaxy. And there are several ideas. So maybe this cluster was formed there, or maybe it arrived from somewhere, or maybe it was there and was rejuvenated by collisions of the stars, like it happens in globular clusters.
How does it compare with other galaxies, spiral galaxies? Is this phenomenon seen in other galaxies?
Well, the problem is that, there are clusters, yes, but the problem is the distance. So we cannot resolve stars in our galaxies, yeah? So we only can measure, let's say, the combined light.
But with other galaxies, we see some other spiral galaxies.
Yes, there are clusters. There are clusters too,
Of young stars.
surrounding the black hole, or in the vicinity of the central black
I
hole.
think it's really difficult to disentangle. So from the spectral analysis, there is a suggestion that you have some younger stars as well. But it's really impossible to say that younger are closer to the black hole and the older are farther out. You see the composition, you do not see the resolved image.
So this is the big advantage of our galaxy, that we can resolve stars. Because, well, in Andromeda you can resolve stars, but not faint stars. And from near-infrared observations from the early beginning of the 90s, we measure movements of the stars very close to the black hole, and one of the stars closed its orbit after 18 years. I think there's another one that closed the orbit now, recently. And
The orbit around the black hole.
yes. So the Sagittarius A star is here, and as you can see, its location is not accurately known, and there are pluses. I mean, the positions of this radio source. It's because there are bursts observed. And then you can see that this ellipse.
This is not orbiting the black hole.
No. Sagittarius A star is identified with the central black hole, and the stars, it is not observed in the optical in.
So this ellipse is
So what goes on the ellipse? And where is this?
Just-
the black hole is where Sagittarius.
So the black hole is here.
This is here.
So it's like in approximate way the Kepler
Orbit.
Yes.
It's highly.
It's good to know.
But you look see it from
But what moves around?
well, stars, young blue stars of this nuclear star cluster.
Cluster of young
Bunch of young stars.
but it does not look like a focus of the ellipse.
Yes, yes.
Because you're looking at the projection from a different plane.
Yes,
Ah, could be.
this is the projection, and
What about
and you have.
If you just include a little bit, you can see it as a circle.
And so this is another star here, and another star closing its orbit around the center here. And from about 30 stars monitored for over 25 years, we can estimate the mass of the central black hole. And so these are the projected orbits, and these are locations of the orbits in the sphere here. So for example, you can see that the young stars marked in blue here remember their momentum, the orientation of the orbits. Okay, so and this is that we know that the central black hole is more than 4 million solar masses. But there are problems. It's not easy to, as I said in the beginning, to observe the galactic center. It's because Sagittarius A star is a faint scatter source, and at different wavelengths, the size of the source changes. So what we can say that the diameter of the source is smaller than 1 astronomical unit. And another thing is that we can measure its proper motion, because our sun revolves the center, and we can see year after year the different location of this source. And there is also uncertainty for this
Are there
measurement.
any estimates of the merger of these with the central black hole, so we could see nice gravitational radiation from our own galaxy? Because they must merge
Well,
eventually, because they.
You mean the stars with the black hole?
Yes.
Or it's not
Maybe,
so,
but
because the
not yet.
closest,
Well,
distance is 2000 gravitational radius.
the closest
So-
star.
Yeah,
Okay.
the passage, the smallest star, periastron is 2000 gravitational radius, so it's not really very close.
Yes, but they were orbiting for many, many millions of years, so they dissipated energy and they should be falling on the black hole.
This will be a slow process.
Yeah.
Yeah, it may be Hubble
But we have a lot of time.
Yes.
slow as compared to
Yeah,
what?
maybe it's slow, but we have a lot
As
of
compared to
time.
what?
Especially since some of
To
them
my life.
float.
And this was the here I show you the evidence for the massive objects at the center of our galaxy from the 70s, from measurements of the radial velocity of gas in the vicinity of Sagittarius A star. And I mentioned about the pluses. So we observe flares in this source in X-rays, in near infrared, and in radio. And this is not the same period of time, but the scale is similar, is the same. So from this we know that the time scale of the outburst is about 2.5 hours. But we don't know what is the reason for the outburst. So one idea is maybe that some asteroids fall onto the surface, on the hit the black hole. And now, how far is the galactic center? And in astronomy, measuring distances is really far, since we receive practically only the light from distant objects. And there are many methods, but most of them are inaccurate, and measuring distances is not easy. So, for example, you can measure the distance to the Sagittarius A star using trigonometric method, just simply by looking where the star is located as the Earth moves or revolves the Sun. But for this, you need to find a background source, a background object. And this object, this is seen in radio, is a extragalactic source. But the problem here is that this source and this source both are faint, scattered, and so that's why the uncertainty is large. Other methods based on model of the galaxy. So, for example, we are looking for some objects in the galactic disks. We measure the velocity and assume kinematic of the whole Milky Way of the disk. And, for example, one of the results is shown here.
The effects of dark.
Yeah, of course, yes. So, for example, here you see that so this is the velocity curve. You can see that is more or less flat. So another assumption right here, and a result maybe not very fresh, but you can see the error is not so small. And another option is to use variable stars as standard candles. So you are looking for special variables like pulsating variables, R-Lyrae type stars, or Delta Cephei type stars, and then you do some assumptions that we observe this kind of stars in other locations, and that you assume that they emit the amount of light from models, from observations of other locations in the sky. So the problem is here again that we have a lot of dust close to the galactic plane, so it hampers the proper measurement of the distance, while we see, for example, very well large Magellanic Clouds and pulsating stars, standard candles there. But the problem is that this is a different population in Magellanic Clouds or different galaxies. The chemical composition of that stars is different. So there are many assumptions to measure distances with variable stars. So this is a kind of indirect method to measure the center, to measure the distance to the galactic center. And well, these are people attempts to measure the distance to the center over the last century. So the first measurement was made by Harlow Shapley with globular clusters. So he found that globular clusters are in the galactic halo, and we are off the center quite much. So 11 kiloparsecs from us was the first measurement. And then different methods. So, for example, variable stars, some standard candles like masers, red clump stars, and other methods. And you can see two horizontal lines here. So these are recommendations from the International Astronomical Union that in the 70s it was 10 kiloparsecs away, and now it's 8.5. But you can see that most of the points are below this line, so it should be changed.
Time is not always.
And now is about. Okay, and you must have noticed the bar in the galactic center, And the evidence, the final evidence, came from the Ogle data, early 90s. And here you can see stars from one of the fields toward the galactic bulge. This is the so-called color magnitude diagram. You can see main sequence stars. So these are stars that burn hydrogen in their cores. And then stars evolve. And at the phase of evolution in which the helium core is burned, the helium is burnt in the core, then the stars stop for a while, well, for a longer time again here, and this is the so-called red clump, because these are red giants, and observations of red clump stars at different location in galactic latitude, so this is about 5-6 degrees on the, to the let's say left and right from the galactic center, brought this result. So there are differences in magnitude, in brightness of these stars, which comes from different distance to the one end and the other end of this bar. So, and this was found and published by Krzysztof Stanek in the early 90s, based on Ogle 1 data. This is a plot from a paper based on Ogle 2 data. So there was this, as you can see, results of fitting ellipsoid to the bar. Although now we call that the bar is rather boxy than elliptical. And also the evidence in the bar was in the COBE data. COBE observed not only the microwave background, but also at shorter wavelengths, 2.2 micrometers in the Derby experiment. And you can see that this left side is thicker than the right side. So we have this we can see that there is a bar inclined with respect to the line of sight from us, from the sun to the galactic center. And there was also something incorrect in the early years of looking for microlensing events. So the number of observed microlensing events was too high. And was too high once people assumed spherical distribution of the central part. So another evidence for the inclined bar, let's say towards us. And what's the age of the bulge? So astronomers use isochrons, modeled isochrons, and this is again the color magnitude diagrams from a very, very deep Hubble field. But this is toward the bulge, and so this is the galactic disk stars and the bulge stars, and the best fit is 10 gigayears. So the galactic bulge is 10 gigayears old, and the error is about 1 gigayear. And this is metallicity. So the iron over hydrogen abundance, and this is assumed that this is more or less solar. So this is logarithm of the amount of metals to hydrogen. But I said that there is that the galactic bulge is old, but the nuclear besides the nuclear star cluster, there are also young objects. So, for example, classical Cepheids are present somewhere also in the galactic disk. So they are young objects of about a few hundred million years. And then there are supernovae. So the youngest supernova in our galaxy wasn't observed, and it was found later after observations in X-rays and radio of this source, and it was in about 100 years ago. So the youngest supernova. And well, I showed you that there is a bar.
It was not directly observed.
No, it wasn't. No. It wasn't because of the high reddening in the optical. It's seen right now only in X-rays and radio. Another thing is that maybe there is a smaller bar called secondary bar in the center, but this is not proved. Because these things are observed in other galaxies. So these are examples of other galaxies where you can see one bar and there another smaller bar inside. And another thing is that galactic halo and old stars. So old stars are also very, very old stars. I mean, not only the few giga years old stars, but older stars are present everywhere, and they concentrate toward the center. And these stars are called R-Lyrae stars. These are pulsating stars, easily recognizable because of their characteristic light curves, and we know that they are old from models. So these are core helium burning stars, relatively bright, and that's why quite easily observable in the center. And Ogle in the optical has discovered many thousands of such stars in the galactic bulge. And now a few words about Ogle right now. So today is a great day for us. So exactly 25 years ago, Ogle started observing. So it was April the 12th, 1992. And right now we are in the fourth phase with wide field camera. Well, observing, monitoring galactic bulge, galactic disk, and Magellanic clouds, and discovering periodic objects, discovering non-periodic objects like transients, novae, supernovae, and microlensing events. And about 1 million variable stars have been discovered and classified, including the R-Lyrae stars. And for this occasion, I mean the 25 years, we are organizing the conference, and this will be held in Warsaw in the last week of July. So if you are interested, please welcome. Okay, and this is the team right now. PI is Professor Andrzej Łudalski at the Warsaw University Observatory, and well, the initial idea was to find microlensing events. I will not tell much about it here. And the Ogle telescope is located at Las Campanas Observatory, so this is the southern edge of the Atacama Desert. And this is a satellite image, but I can tell you that really the sky there is very clear all over the year. So we counted that on average about 330 nights clear with useful data. Okay, so there are also clouds, of course, sometimes, and the weather is not fortunate every night, but 330 is a huge number, comparing, for example, to Poland, where we have 100 such nights. And this is the Las Campanas Observatory. And in Ogle 4, we observed the galactic bulge with different cadence. So cadence is okay, here you have the number of observations per night, but in some cases we observe the same field every 20 minutes. So this is here is the galactic plane. And as you can see, we observe the area where the probability for microlensing is the highest. So that's why we concentrate on this area where the density of stars is the highest. And now back to our Lyrae stars. So about 40,000 Lyrae stars have been discovered by Ogle 4, and this is the map of these stars in galactic coordinates. So you have longitude, latitude, and the colors here mark brightness of the stars. So you can see closer to the galactic plane, you see fainter and fainter stars, less and less stars, and here nothing because of the dust. And I was working on this sample and trying to find what's the distribution of these old stars. So these stars are older than the bar. They are something like 12 or 13 giga-years old. So these are first stars, probably stars that arrived from other accreted galaxies, dwarf galaxies that later formed our Milky Way. So from these stars we can learn something what was in the early history of our galaxy. And so I worked on this sample and found that the population of these stars is flattened, just in the sky. But of course, the most interesting thing is what happens in in 3 dimensions. So measuring distances here is very important. And well, the formula are very simple, but there are many assumptions behind them, and some empirical relations, and the question on true reddening is still here. So this map comes from an infrared survey and was used here to measure the distances to each star, to each Lyrae star. And this is the distribution of these stars, and the distance I found to the center of the whole populations, which coincides with the galactic center of our galaxy. And these are the most recent measurements of the distance to the galactic center. And well, as you can see, this is below 8.5, the horizontal line. And this is the most recent distance from the dynamics of the stars in the nuclear star cluster. So 4.3 million solar masses is estimated for the central black hole, and 8.3 kiloparsecs.
And they have very low systematic errors.
Yes, I think this is thanks to this long period of observations. So now it's about 25 years. So 1992 was the first measurement.
Can you also cover these 3 last methods are completely independent from each other, yes? 8
Yes, they are independent. Very similar, but but measuring is not easy. As I say, there are some assumptions. So, but probably this the method of the future that or the method that will give us the true distance to the galactic center is probably the trigonometric method, but after maybe some improvements of the technique. So this is the hope, that probably this trigonometric method. And okay, and so these are these Ogle Lyrae stars, and I checked what's the distribution, divided the area in the sky, and checked what's the distribution along the line of sight, the 4 line of sight, and you can see that constant density lines form ellipses, or something very, very close to ellipses. These are not circles. And from this, and from the information on flattening in the sky, I found the following parameters: the axis ratio of the ellipsoid of the old stars ellipsoid, and this is the inclination of this bar. So we are at 0, 0 at the beginning of the system. This is in the galactic plane. This is projection onto the galactic plane, and the sun is below there. Because so these are the lines of sight from us. Yeah. And the ellipse is inclined, and this angle is quite similar, or probably the same with the orientation of the whole bar. So the bar is very massive, and old stars in the galactic the galactic bulge, the very old stars form a less massive component. But in the very center, they form also this inclined structure. And this was recently confirmed by modeling of the old bulge in the more massive, in the gravitational potential of the massive bar, and indeed we must see an ellipsoid. So these are axis ratios. And then was another interesting discovery from Ogle data. So this is a very simple plot. You can see period of the stars because they are pulsating stars, and amplitude, and you can see 2 close sequences, and this is interpreted as the presence of 2 slightly different populations. So 2 different populations that differ by chemical composition, slight difference in chemical composition. So there's an idea that maybe these stars come from 2 big galaxies that merged and formed our galaxy.
Of comparable mass, right?
Of comparable mass, yes. Yeah. And also there are stars here, so probably these are these stars are from different. So this was before, in the early epoch, let's say, of this hierarchical model of formation of our galaxy. Well, this was more quantitative way of estimating, let's say, the abundance of the two populations named A, B. And then we can measure from these stars metallicity, so we can see how the amount of metals changes from the galactic center radially. So you can see that in these old stars, very old stars, the amount of metals is more or less constant, and then it drops around the distance of the sun, more or less, from the galactic center. Density profile was unexpectedly simple for these old stars, so just a pure power law. And this is the most recent 3D view of these old stars from Ogle. So you can see this. So we are here, where is the red X, and you can see that these stars form this ellipsoid, and here you can see another cluster of these stars, and this is the Sagittarius dwarf spheroidal galaxy in the background. So here we are. Here is the galactic center, it is not seen by us because this is close to the galactic plane, and the Sagittarius dwarf is disrupted. And with these stars, we also measured the distance to the Sagittarius dwarf with my student. Okay, and actually, this is what I said here is compiled. So the distance to the galactic center from RLR stars, and that they form this elongated structure, and that there are these two, at least two populations. And well, there are many questions referring to the galactic bulge. Of course, what's the distribution of these stars, of RLR stars in the galactic center, because we don't see them in the optical. And of course the question on kinematics, because from photometric information we cannot say nothing about movements of the stars. And now there are different photometric as well as spectroscopic surveys of the stars in the galactic bulge, focusing not only on RLR stars but also on these bar stars, red clump stars. And this is the current Ogle 4 chart. So one small piece here is the Ogle camera. This is about 7 moon area. So we observe this area in one image. There is also an infrared survey of the galactic center, and this is ESO. This is this European Southern Observatory Parnell Observatory, and there is a 4-meter telescope for surveys with an infrared camera. And with this we can see, with these telescopes and this camera, we can see what is going on behind the clouds, hopefully. Okay, and now questions referring to the galactic bulge. So, well, what's the distance? What are the parameters of the central black hole? Although they are now more and more accurate. And then what is the past? What formed? How the nuclear cluster was formed, and questions about the galactic bar, and what's the true size of the bar, and for stellar populations forming the galactic bulge. This is the most complex, I would say, component of the Milky Way. Then, if we go outside, we have the galactic halo, and in the galactic halo, we have substructures, as I will as I will show you, and what we are not sure is what is the shape of the galactic halo, and how the galactic halo was formed. So, for example, there is a hint that maybe there are 2 populations in the galactic halo. So this is from the Sloan Digital Sky Survey view. This is a big portion of the sky. So you can see here the streams over densities in the galactic halo. So this is the evidence for the continuous formation of the Milky Way, that small galaxies, dwarf galaxies, are accreted all the time, are disrupted, the ones that are close to us. And questions referring to the galactic halo, the big question is what's the percentage of stars that was born here, and the percentage of stars that came here from outside with other galaxies later. And of course the question on dark matter, but I concentrate my talk only on luminous stars, on luminous matter. Okay, and now we are in the galactic disk. So from observations of stars in the solar neighborhood, people found that there are stars from the galactic thin disk, thick disk, and halo, so they have different distributions. So 0 means here the galactic plane, and this is the distributions of different stars at different elevation, let's say, from the galactic plane. And this is how to distinguish between the populations, because stars are mixed, so stars from the halo and from the disk are mixed, but we can distinguish them by metallicity, by measuring the amount of metals in the stars, and also from kinematics, of course, because halo stars are on wide orbits, not at the galactic plane. And then there are also works on how to distinguish thick and thin disk stars, because they are kinematically different, not very much. And what differs probably is the abundance of alpha elements in these stars. But this is still, there are still works on it. And the difference in kinematics here for thin and thick disk stars in different directions. Okay, and now the spiral structure. So this was from the near infrared, this visual, this artist impression, as I call. So this is from counting the stars in mid-infrared observations, and the cusps here mark the location of the tangent directions to the spiral arms. So this artist impression is based on true observations, of course. And the authors found that very likely there are two spiral arms in our two main spiral arms, starting from the edge of the bar. Yeah? But also we know that there are other arms, and so we are not sure how many arms do we have in our galaxy. So for example, these are maps from hydrogen observations, neutral hydrogen observations in 21 centimeters, and these are observations from the location of open clusters. So there are also differences. For example, here you can see that there are 4 arms, relatively strong, comparatively strong. And how big is our galaxy? So the edge of the galactic disk is about 14 kiloparsecs from the galactic center. Our sun is, well, here was an assumption of 8, it's 8.3, so we are more than halfway from the galactic center. And there are also outer arms, but this is still, we are not sure what's further out there. On the other side, of course, even more difficult. And classical civets are the young objects which that may help us to see what's the structure of the disk in our galaxy. But so far, as you can see, is not easy. We can see that they form a stripe and let's say curved stripe, but this is not very strong. And some more numbers. So this is the estimated elevation of the sun above the galactic plane. We are not exactly in the galactic plane, but slightly above. And if we assume the number of spiral arms, that this is the pitch angle of the spiral, and the rotation of the spiral pattern is here. Another thing from Cepheids we can estimate is the metallicity gradient. So in the galactic disk, further from the center, the stars are less abundant in metals. So that's why you can see the decrease. And galactic warp is another strange thing we have in our Milky Way. So the galactic disk is not perfectly flat, it's curved. There is a warp, and maybe it's not seen here, but this is not this is not really straight here. So maybe this is seen in Cepheids, but in hydrogen you can see better that the curve. It's not flat. So this is the whole sphere, right? Okay, and this warp is a real structure seen also in stars, in the distribution of young stars like pulsars, OB-type stars, classical Cepheid stars. And proposed explanation, well, probably gravitational interaction or influence of neighbors, galactic neighbors to our Milky Way. And this is probably one of the most recent plot of the velocity curve. So you can see that it's flat, and well, this is from different, again, methods of measuring the velocity. And there are models of our galaxy. Maybe I will skip a little bit. So there are many assumptions, and the models are not perfect. So what I want to tell you here is that, okay, so we have the galactic bulge, stellar halo, and then we have disk, and you can see that there is not one, there's, okay, probably maybe one thick disk, but there were bursts of formation later, so that's why there are many younger components, for example, in this model. And so you can see these components here. What are the ingredients for the velocity? And the total, as you can see, is flat. And some another results from Ogle, this time from the third phase. So I looked for any kind of interesting objects, variable objects in that direction. This is 60 degrees off the galactic center, this location, and I found some classical Cepheids, and these classical Cepheids will be used to find what's the structure of the stars in the galactic disk. So this is the location of classical Cepheids in the sky, and this area is observed by Ogle, and Ogle 4 is in red, Ogle 3 so already checked is in green. So this is the Ogle sky again, and these are the most recent findings. So R-Lyrae stars in this stripe of the Milky Way, and classical Cepheids. But this is very fresh, so I cannot show you anything else on the galactic structure yet. And questions referring to the galactic disk. So how the disk was formed, and how many spiral arms do we have? 2 or 4? And of course, what forms the galactic warp? Okay, thank you.
Does the motion of the solar system around the center of the galaxy agrees with the rotational curve? Because this is known from the...
Well, there has been some corrections. So it was 220 and now it is 240 kilometers per kilometers per second. Yeah.
The motion of the solar system. So there was a size of correction. And this requires the dark.
Yeah. Yes.
So the dynamics of the stars in the central parts is, in the case of old stars, this is kind of relaxed, right? So it shows.
Yes. Yeah, it's
Only
relaxed.
in the case of the younger stars, you still may trace some kind of origin. On the other hand, at larger distance, you can still trace initial angular momentum of those inflowing things, right?
Maybe, but actually I don't know whether.
Spiral structure, how old is actually spiral structure? This is something which was
Well, the
formed
galactic.
immediately.
The galactic disk is believed to be slightly older than the galactic bulge. So it's more or less 11 giga-years
And this structure was
old.
present from the beginning always? Or it's
Probably yes. Yeah. And it is believed that the galactic bulge was formed after the galactic disk. So the stars and gas probably still flows in from the disk to the galactic bulge. Maybe not much amount, but one of the idea is that the gas comes from the disk due to rotation, and that's why this cluster, this nuclear cluster is fueled by this gas from the disk. Probably.
I have a question about this metallicity. You showed this metallicity profile with radius.
Yeah.
Yes, and do I understand correctly? There is more metal-rich stars in the bulge.
Well, no. Well,
How is that?
so this is for galactic disk. So we don't go very deep, let's say, to the center. Yeah. This is only for the disk.
But you see some trends. It's not flat.
No, it's not flat. Yeah, it's less and less metals with the distance, increasing distance from the center.
So you have some old stars farther out, yes.
Yes, but this refers to young population only. Yes, so
Yeah, but
you
still,
cannot
if you
mix
have
everything.
less dense surrounding, you do not have this option to process the material several times, right? Which increases the metallicity.
Yeah, maybe, but this is still not known.
Low density surrounding, you have no chance to reprocess. It's quite natural.
So there is a lot of work here to be done.
Well, yes.
There's a lot of stars.